Welcome to Descriptive Statistics. Today we are going to explore one of the most fundamental and powerful concepts in all of probability, the random variable. If you have ever wondered how mathematicians take chaotic, unpredictable real-world events and turn them into clean equations, this is the secret. We will learn exactly how to translate these physical outcomes into numbers we can actually work with, building your understanding from the ground up. To begin, imagine you are a referee at a sports game. Your only job is to write down a single number at the end, like the total points scored or the winning time. You are taking a complex event and summarizing it with one number. That is exactly what a random variable does. It is a translation machine. Formally, it is a measurable function mapping a sample space to real numbers. The term measurable means we can trace any number it produces back to an event in a sigma algebra, which is just a well-organized collection of events that have defined probabilities. This prevents mathematical paradoxes. Now that we understand the idea, let us look at the mathematical notation. The formula on screen shows how this translation works. The capital X represents our random variable. The symbol omega represents the sample space, which is the complete set of all possible physical outcomes of our experiment. The arrow simply means maps to. Finally, the R represents the set of all real numbers. So, as the physical outcome in omega changes, the real number that X produces will also change. This simple mapping is the bridge between the physical world and mathematics. With the general definition established, let us look at the first specific type, the discrete random variable. Think of this like climbing a staircase. You can stand on the first step or the second step, but you cannot stand on the 1.5 step. Discrete variables take on specific, separated values with gaps between them. You are counting things, not measuring them. Examples include the number of cars in a parking lot or the number of heads in coin flips. Because the values are separated, we can list them out one by one. To describe the probabilities of these specific discrete values, we use a probability mass function. In this equation, the capital X is the name of our random variable, while the lowercase x is a specific number we are checking. The function p of x gives us the exact probability that our random variable will equal that specific number. A crucial rule here is that if we add up p of x for every possible value of x, the total must always equal exactly 1. This ensures our model accounts for every possible outcome, which is a strict requirement for any valid probability distribution. Let us see this formula in action with a concrete example. Suppose we flip a fair coin 3 times. We define our random variable x as the total number of heads we get. We want to find the probability that x equals 2. First, we need to find the sample space, which is all possible combinations of 3 flips. As shown, there are exactly 8 possible outcomes, ranging from 3 heads to 3 tails. Listing every single possibility ensures our probability calculations will be perfectly accurate. Continuing with our coin flips, we know our discrete random variable x can only take the values 0, 1, 2 or 3. We look at our sample space of 8 outcomes and count exactly 3 combinations that have exactly 2 heads. Heads, heads, tails, heads, tails, heads, and tails, heads, heads. Since there are 8 total equally likely outcomes, we divide 3 by 8. This gives us a 37.5% chance of getting exactly 2 heads. This step-by-step counting method works perfectly for discrete variables. Now that we have mastered discrete variables, let us move to continuous random variables. Think of this like sliding your hand up a smooth ramp instead of climbing stairs. Your hand passes through every single microscopic height along the way. Here, you are measuring things, not counting them, like the exact weight of an apple or the time it takes to run a mile. Because there are infinitely many possible decimal values between any two numbers, the probability of hitting one exact infinitely precise number is actually zero. Because the probability of an exact number is zero, we must calculate the probability that the variable falls within a certain range. We do this using a probability density function, denoted as f of x. This function draws a curve representing how the probabilities are distributed. The symbols a and b are the lower and upper limits of the range we are interested in. The integral symbol means we are calculating the total area under the probability curve between a and b. As the gap between A and B gets wider, the area increases and therefore the probability increases. To make this concept concrete, let us look at this diagram. You are seeing a bell-shaped probability density curve. The horizontal axis represents the values of our continuous random variable x, and the vertical axis is the density f of x. Notice the blue shaded region between points A and B. Instead of looking at the height of the curve at one specific point, we look at this shaded area. The total area under the entire curve is always exactly 1. The size of the blue region is the probability we just calculated with our integral. Let us apply this integral to a real-world scenario. A train arrives exactly every 10 minutes, and you walk into the station at a completely random time. Let x be your waiting time in minutes. What is the probability you wait between 2 and 5 minutes? Since you arrive at a random time, your wait is uniformly distributed between 0 and 10 minutes. The total area must be 1, so a rectangle with a width of 10 must have a constant height of 1 divided by 10. This flat line is our probability density function. With our density function established, we set up our integral to find the area under the curve, specifically between the 2-minute mark and the 5-minute mark. We integrate the constant function 1/10 with respect to x. The mathematical integration of a constant number is simply that constant multiplied by the variable x. We place this result inside brackets to show that we still need to evaluate it at our upper limit of 5 and our lower limit of 2. This is a standard calculus step for finding areas. Finally, we substitute our upper limit of 5 and our lower limit of 2 into the integrated function. We subtract the lower value from the upper value, which gives us 3/10 or 0.3. This translates to a 30% probability. This makes perfect intuitive sense. The window of time between 2 and 5 minutes is exactly 3 minutes long. Since 3 minutes is exactly 30% of the total 10-minute waiting period, our mathematical result perfectly matches the physical reality of the situation. We have seen discrete and continuous variables, but sometimes a random variable is a mix of both. A mixed random variable has some specific exact values that happen with a discrete probability, but it also has ranges of continuous values. Imagine a bucket outside. Sometimes it is completely empty, but when it rains, it fills up with a continuous amount of water. The chance of it being exactly empty is a discrete jump, but the amount of water it holds when it is not empty is a continuous measurement. To represent a mixed random variable mathematically, we must combine our approaches. We cannot use just a continuous density function because there might be a massive spike of probability at one specific number. For instance, in our upcoming salary example, the equation on screen represents the discrete part of our mixed random variable. The probability that x equals 0 is exactly 0.10. We state this as a discrete mass because the area of a single point in an integral is 0. This handles the exact values perfectly. Let us look at the full example regarding salary data with unemployment. Consider a study on the monthly income of adults in a city. We let X be the monthly income in dollars. We are given that 10% of the population is unemployed and earns exactly $0. The remaining 90% earn a continuous range of salaries greater than 0. We need to represent this entire situation mathematically, combining what we know about both discrete and continuous variables. Continuing with our salary data, we already established the discrete part for the unemployed population. Now we must account for the employed population. We use an integral for the continuous part of our mixed random variable. The function f of x represents the smooth distribution of salaries for all employed people. The total area under this continuous curve from 0 to infinity must equal 0.90. By combining these two equations, we create a complete mixed distribution model that accurately reflects the real-world economic data. We have covered a lot of ground today. Remember the three main takeaways. First, discrete variables count separated values, like stairs, using a probability mass function. Second, continuous variables measure smooth ranges, like a ramp, using a probability density function and integrals. Third, mixed variables combine both approaches. Mastering these distinctions is the foundation of all statistical modeling. Choosing the correct mathematical tool ensures your models will accurately predict real-world outcomes, from weather patterns to financial markets. Great job following along.